Am I audible?
There's some background noise.
Sorry?
There's some background noise.
Oh, is it still there?
I think it's fine.
Okay. If it is still there, please stop me. It's raining here, so probably that is
It's fine now.
okay. We'll just wait for one more minute and then start. Till then, I'll just make sure I have the basic imports in place. Okay, so I think it's time to start. Okay, so I have just imported the usual libraries and the basic setting is there. So now what we are going to do is going to try and reproduce the whole ANN code, but I'm not sure how error free it will be. I'll try my best to recreate that, but certain places I may have to refer to the original the base collab. Okay, so yeah, now what we need is we'll work with the MNIST dataset. Okay, so SKLN has a version of the MNIST dataset. So we'll first go ahead and load that. Scaling dot datasets. We have it is load digits, right? So I hope you all know how to. If you press tab, then you'll know what all you can input. I hope you all know that, right? So and if you want to know what the attributes or methods of an object are, same thing will work. In case you are not aware of that. Okay, so load digits is apparently a function. So okay, so this is digits. Now digits has basically two features that we are interested in. One is the images and the other is the labels, right? So I'm going to call this X and I'm going to call that labels Y. Labels are uh, the target, right? So it's the target. So that is those are the labels. So let's just first thing that we'll do now is see what the shapes are. This thing has 1700 roughly 1800 images, and they are of size 8 cross 8, right? So there are totally 64 pixels and it's an 8 cross 8 image. The labels will be just the number of, maybe a vector of size 179, right? So I want to keep track of this number, so I'll just go ahead and print it, right? So that is the images. So what we'll now do is we'll not stop here. We, since they are images, we can actually visualize them, right? So I'm going to take, say, the first image in the data set, and that will be an 8 cross 8 image, right? So that will be an 8 cross 8 image. So this array I'm going to visualize using matplotlib. So plt.im show image show. So I want it to show the image. Okay, so this is actually a 0, but because of the very small number of pixels, it looks so messy. But we'll also print along with this what y of 0 is, just to confirm that this is a 0. Okay, so this is indeed a 0. Maybe let's see what, say, the 100th image looks like. Sorry, 100th image, not 1000. Okay, so it's a 1, it's a 4. It doesn't look like that, but yeah. So these are the images that we'll be working with, 8 cross 8. And so ideally we are supposed to do this all train test split and all that, but since we are only going through kind of a demonstration of neural networks, I'm not going to split it. I'm just going to retain x and y as they are. Should not do this in practice, but this is just to make life simpler. Okay, so any questions so far in loading the data set? Okay, I hope there are none. So what we'll do next is, see, there are a sequence of things that we have to do, right? So we have to, the main things that we need to do are write code for the forward pass, backward pass, right? And you have to fit your model, but fit will make use of every time you are fitting a neural network to your data. For each epoch, you will have to do one forward pass and you'll have to do one backward pass, right? So your fit function or fit method will have to use these two. Okay, so but even before all that, we need to initialize the network, right? So probably network initialization comes first. So you have to initialize your network, right? And then forward pass, and then backward pass, and then finally you can fit your model. Okay, so this will be roughly the process that we'll follow. All right, so first thing is you have to initialize the network, right? So we have to ask these questions, which are following, right? So how do we represent the layers? That is one question. How do we represent the weights? Okay, how do we keep track of the number of neurons in each layer, right? So these are all some very basic questions. Unless we answer them, we'll not be able to come up with this architecture, the network architecture, right? So the basic thing that we are going to do is we are going to keep track of the layers and the number of neurons as a list, right? So the first two things, right, representing layers and keeping track of the number of neurons, we'll do that using a simple list like this. Okay, and so let's say you have a 3-layer network which has 10 input neurons and say 100 hidden layer neurons and 3 output neurons. Then your list will look something like this. Okay, so this completely specifies both the number of layers and the number of neurons in each layer. Now, once we have this, what do we do next? Any suggestions for what we have to do moving forward?
Initialize the parameters.
Okay, we'll have to initialize the parameters, right? So, okay, we'll have to initialize the parameters. So for that, what we're going to do is we are going to follow a slightly different approach. We are first going to count the number of parameters, right? So that's what I'm going to do now. I'm going to first count how many parameters my network has, right? And for that, the only argument that I need is the list S, right? Once I know the list S, then I know exactly how many layers are there and how many neurons are there in each layer. So that is all I need, right? So this is what we'll be doing first, counting the number of parameters in the network. Okay, so can someone tell me how to proceed from here? How do we count the params?
Multiply like the like if you start from 0 indexing, we'll multiply like the I plus 1th element with the I minus, like ith element with the I minus 1th element, and like keep that, sum that up and then loop.
Okay, well that's a good way, right? So you start from layer, you index the layers as L, like this is what we did, remember? So S of L will be the number of neurons in layer L. So you start from the first hidden layer. L equal to 1 is the first hidden layer, and you go all the way till the last layer, right? Say the number of layers are capital L equal to length of S, right? So you start from the first hidden layer and you go all the way up till capital L minus 1, and
number of layers is 113, right? No, because there are 100 hidden layers.
No. So these are the there are 3 layers. These are the number of neurons in each.
Oh, neurons. Okay. Got it.
Okay, so let's say params. This is the count, right? I store the count here. So I first let's do the weights, then the biases. So how many weights do I have in at layer L? The weight matrix is WL. So how many parameters does it contribute?
100 times 10.
100 times 10, right? So it is S of L into S of L minus 1. So if you recall the slides, WL is the weight matrix at layer L and it is of size. Is it showing this?
For L in range.
Oh, okay. Super. See, this collab never makes a mistake. We only make mistakes. So I was wondering what was wrong. Okay, so this is the contribution of the weights, right? So this is S of L cross, sorry, S of L minus 1 cross S of L. That is the weight matrix. Now, the bias at layer L will be having what shape?
It would be a vector of L cross
It will be a vector of
1 dimensions.
Yeah, right. So it will just have as many neurons as there are in layer L, right? So the bias part is just S of L. Now, is that complete, or have we missed something?
So I did not understand the weights part, like why we multiply.
So there are see, if you have 10 input layer neurons and 100 hidden layer neurons, then number of parameters are 10 into 100, right? Number of parameters in that weight matrix connecting this layer and this layer, it is 10 cross 100, right? That is the weight matrix. If you recall the slides, whatever we saw.
Yes.
So that is why we are doing this product of S of L. Okay, so it's the same, but it's better to write it this way. Okay, so let's just run it and see if we are getting the correct answer. So 10 into 100, 1000 parameters from the weight matrix plus 100, right? So that's 1100. And then you add 300 to that. So 1400 plus 3. So 1403. That many parameters are there in our network. Okay, so we have taken care of these two parts. Now next thing that we need to do is compute the rather initialize the weights, right? So again, I need to have the network structure, network architecture. Okay, I'll also invoke count params here so that it gives me the number of params. Right, so far, are there any questions? I think this would have been quite straightforward for most of you. Okay, so see now comes kind of the tricky part in the whole AN class. I'll just show you that image that is required. Okay, so how many of you understood this image would have been absent, unfortunately, in the slides? I was supposed to include it, but it somehow got excluded from the collab recording. So let's say you have a weight matrix in some layer. Let's say, so it will be easier to visualize this if we have it this way. Whatever, right? So you have one layer having 2 neurons and another layer having 3 neurons. Okay, so your weight matrix connecting those 2 layers will have 6 weights, right? So 2 cross 3. So think about that weight matrix, and what we are essentially doing is flattening this matrix and converting it into a vector of parameters. Okay, do you see what this operation is doing? If you have a weight matrix of size 2 cross 3 having 6 parameters, I'm just representing it alternate in a different manner as a vector of 6 values. Okay, so do you all get why we are doing this? Why this?
Why we are doing, I'm not able to get, but what we are doing, I'm able to get.
Okay. Yeah, fair enough. So what we are doing, if for now, if it's okay if we have the idea of what we are doing, right? So I hope that is clear, right? What we are doing for everyone. Okay. Okay. So please stay with me. So what I'm going to do is there are, say, I just run this so that I have some concrete number to work with. So there are 29 parameters. Assume there are 29 parameters in your network. Okay, 29 parameters. So I'm going to initialize. After all, there are, if you think about this neural network as from a very high abstracted point of view, it has 29 values to play around with, right? So these are the things that you can modify and adjust so that your network learns something from the data. So you are given 29 values that you have to learn from your data, right? So what I'm going to do is I'm going to initialize a vector of 29 values. Okay, so I use the standard normal distribution for this. Do we have normal? Okay, so stay with me. I am initializing these number of parameters, and then note that somewhere along this long vector of 29 values, some chunk of it represents the weight matrix from the input layer to the hidden layer. Right. So in this long parameter vector, which I call theta, some portion of it is going to represent one of my weight matrices. Is that idea clear? What we are driving at?
Some portion will be for theta and the rest will be for bias, na?
Some portion will be for W and some portion will be for B.
Yes.
Okay, so I am trying to create a map between my theta and my weights and biases. Okay, so I'll go sequentially, and what I'll do is I'll extract that portion of this vector which corresponds to W. I'll extract that portion of B which corresponds to that portion of theta which corresponds to the biases. I'll do this for each layer. Okay, so let me go ahead and do it, and then maybe we'll have a better idea. Okay, so I'll once again start from 1, this is a number of layers. Okay, so your weight matrix, first weight matrix is of shape S of L minus 1 into S of L. Okay, so these many parameters from theta I am going to extract. Okay, so this is kind of a slightly complicated code, so I don't know how to make it simple, but you'll have to stick with me on this. Okay, so do you understand what I have done in line number 8?
Took a partition of the theta vector and reshaped it into a
Right.
matrix.
Right. So that is what I have done. So others, are you able to follow what has happened?
So you're extracting a bunch of weights
Yeah.
from that theta that you now initialized.
Yeah.
And the reshaping is
Yeah. So what I have done is I have taken some six elements in theta and I have reshaped it as 2 cross 3.
right. Okay.
Right. So that is what I have done. And in fact, it should be plus equal to, we'll come to all that. So we are initializing the weights, right? So there should be one weight matrix corresponding to each layer. So here, this hidden layer, input to hidden layer has one weight matrix. So hidden layer to output layer has one weight matrix, right? So what I'll do also is that I'll initialize a list of lists, right? And okay, so Again, I hope you all remember all this comprehension business. So what am I going to store in W1B? I'm going to store the weight matrices and the bias vectors, right? So for example, currently it is none, but W of L will be the weight matrix at layer L.
So why is it range of S? Shouldn't it be L?
Sorry, it should be range of L. Correct. You're right. Right. So
Or more specifically, L minus
L
1.
minus 1. Yeah, you're right. So I don't know what I did in the original code, whether I did it for. See, I have used length of layers for a reason. We'll come back to that. But you're right. So the first thing will be none actually, right? So even though you have L elements, the first one assume that it is dummy. Okay, so okay, so what we are doing is this is what we are doing. So this is, I hope the W and B are clear. Now I have reshaped this theta vector. I have extracted the weights from there. And what I'm saying is W of L is this weight matrix. Now I have to take the next chunk in my theta and say that B of L equal to same thing. Only thing is that I won't have to reshape it because it's only a vector. Okay, but before I do that, what thing should I change? What should I change? What should I insert here?
Sir, if we go by the start and end, then I will have in start I will have 0 and in end I will have 6. So then the dimension, there will be some problem in dimension, no sir?
Correct. So I have to modify start and end, right? So you are right. So I have to change start and end so that
Start becomes N plus 1.
start. Yeah, N. Yeah, please go on. Yeah.
Like you should add S of L minus 1 to both of them, I guess.
Okay, S of L minus 1, but yeah, that is right. Now, will start become N plus 1 or will start be just end?
Yeah, it will be just end.
Just end, right? So start will just become N because of the last index not being included, and end should be moved by S of L, right? So the S of L part is the bias. You need this many parameters for the bias at layer L. So this is what you will do, right? And here, notice that I have made one small mistake. It should actually be plus equal to, right? So by my previous end, I need to increment it by this. Okay, so there are probably several other mistakes lurking there, but we'll first. Yeah.
So one question, like the first element of the weight matrix in the bias will always be none, right?
It'll always be none.
Okay, I was actually encountering this error while implementing and I was confused, like
Why we are doing that? Is it?
yeah, like the index error I was getting again and again. I was not doing that none thing. I was doing L minus 1.
Right. See, the rationale is just so that this W of L represents the weights from L minus 1 to L, right? So if I say W of 0, it will be kind of confusing on the mind. So that is why, yeah, you're right. So we will come to that also. In case others didn't follow this part, it's also slightly tricky. So we'll address why this is a range of L and not range of L minus 1. Okay, so this code is wrong. Let me just make it clear right away. We are missing
the
around.
rule starts with 1, I guess that gets taken care of anyway, right? So WL will start with 1 only.
Right.
Okay.
Okay, so we are making some mistakes here. So the way I want to fix them is by having some, by doing some examples. So let's try to see what we have here. Okay. So what is the smallest network I can consider so that it will be easy to debug the code? 2 cross 3. Okay, let's just try doing it with this network. Okay, so what are the errors? This is again, this should be L and not S. Okay, that is the first error. Okay, this is, I have not even initialized end. So let's say start and end both are 0. Okay, what is the next error? Next error is a value error. Cannot resize array of shape array of size 6 into 3 comma 1. Why are we trying to do 3 comma 1?
Race of L starts from 1.
Okay, S of L starts from 2, right? 2. Okay, so what we'll do is the nice way to debug this is to keep printing start and end. Okay, and okay, you can anyone can stop me and tell me where we are going now. So I'll also print the layer info. So we are at layer 1 and start is 0, end is 6. So the first 6 parameters I'm going to reshape it as a 2 cross 3 matrix. So that part is okay. Then start becomes 6 and end becomes 12. That also seems to be correct. No, that doesn't seem to be correct.
We don't have a problem with the length. We have problem with, I think, the dimensions.
Right. So yeah, dimensions. So here, see what is happening is start is not getting. Start should change after this also, right? So start should become
Yeah.
end, right? Start should become end, I believe.
Yes.
Okay, so let's print it once more. This is, I'll say this is for weight and this is for the bias. Okay, so for weight matrix at layer 1, the shape is 2 cross 3. So you start from the 0 point of the vector and the first 6 parameters you reshape it 2 cross 3. Okay, and then we need to do it for the bias. So you start at the sixth parameter in your weight matrix and you take the next 3 parameters, you reshape it as, or rather you retain it as a three element vector, that is for bias at layer 1. Then what you do is you start from the 9th parameter and then you take the next 3 parameters in your theta vector. That becomes your weight matrix for, it's 3 cross 1, but still it's a weight matrix. And then your bias will just be one element. So that is, you start at 12 and you end at 13. Right? So you have 13 parameters which you have partitioned this way. So is this example clear what we have done?
Yes, sir.
Okay, so now to fully appreciate what has happened, I'll just show you why this is such a big deal. And Yeah. So I'm returning theta, W, and B. So I'll also print theta and W, right? Theta and W. Okay. So these print statements are not of that importance. Okay. So these are all random. Just for the sake of, I want to explain something. So for just a brief while, I'll just keep it as zeros. Right? Otherwise, I won't be able to explain these many zeros. Okay, so just hold on. I'll print both theta and W. Okay, I want to print W of 0, W of 1. Right. Okay, so see what we have here is the first weight matrix, which is a 2 cross 3 matrix. That's what is there on the second line. Okay, that is what is there on the second line. And what is there on the first line is the entire parameter vector. Okay, so these 6 values have correspondence with this weight matrix. Okay, so what I'm going to do is I'm going to disturb this theta. First 6 parameters of theta, I'm going to say I'm going to increase all of them by 1. Okay, and now I'm going to print both theta and W again. So do you see what has happened?
It's all inherited.
Right. Okay, so when I change theta, W also changes, but I don't have to explicitly change W. Okay, this is very important. This is why we have been doing all this. So whatever we have done here, this way of partitioning a vector into a matrix like this, by reshaping it, I have done it so that when I change theta, W changes, and when I change W, theta also changes.
Is it because of that list things at dot copy which we used to do?
It is because we are not doing the dot copy.
Okay.
Right? Had we done the dot copy, we would have ended up creating a copy and not a view. So, right? So I strongly urge all of you to look at this reference. But what we have essentially done in reshaping it is created a view. So we are looking at, say, the same Taj Mahal, but from a different angle, right? Just because we are looking at it from a different angle doesn't stop the monument from being itself, right? It just changes your point of view. That's why it's called a view. Okay, so this is still the same set of values. You are looking at it from a different perspective. Okay, so I just want to ensure that B has also been, that's the same thing has happened to B. Let's say, let's take the first bias vector. So first bias vector will be from what units, from what partition is it?
7, 8, 9.
7, 8, 9, right? So rather 6 to 9, right? 6, 7, 8. 0 to 5 will be the first.
Yeah, that's right. Python starts with 0 index, yeah.
Right, so 6, 7, 8. So 6 to 9, and I'm printing my B. Okay, so we see that the bias also undergoes the same thing. Even though we haven't actually reshaped, we have just taken a slice of theta. Okay, so right, so yeah.
So does this are we doing this because of like gradient descent?
Exactly, right. We are doing this because of gradient descent. See, gradient descent is agnostic to what model you are using, right? All the gradient descent needs. Okay, since you, yeah, it's good to it's good to tell you why we are doing this. So when you're writing gradient descent, what are we going to do? We are going to just say move in the direction of my negative direction of my gradient, right? So I'm just going to say theta minus equal to learning rate into gradient of theta. That is all gradient descent cares about, right? So this is what I meant when I said it is agnostic to the model, right? So it could be a logistic regression, it could be, say, linear regression, whatever model you consider, the form of gradient descent is going to be parameter equal to parameter minus learning rate into gradient of loss with respect to parameter, right? So that being the case, we are going to, the same thing holds good for neural networks. So that is why we are separating the parameters into one long vector of weights, one long vector called theta. But for my forward pass, it's much easier if I work with weights and biases. So I still need to keep that view in mind. So I need a mechanism to keep going back and forth between my neural network point of view and my gradient descent point of view. And that bridge or that link is created by this slicing or this view. Okay, do you now understand the rationale behind this partitioning scheme?
So in one update, you can update the weights and biases of all layers.
Exactly. That's the point, right? So in one update, I don't need to do a for loop every time. So rather, I don't need to do a for loop over the layers and update the weights and biases for each layer. I can do it just once for all the parameters, and that would mean all my weights and biases are updated. Okay, is everyone clear?
So effectively, for the purpose of update, we'll be using the flattened one, and for calculation, we'll be using the matrices. Is that how it works?
Yeah. So for the update, basically for the backward pass, where you not for the backward pass, while you're fitting the model to update the weights, you'll be using the theta.
Right.
But for the forward pass, you'll be working only with the W's and V's.
Okay.
Okay. So what we have done so far is just initialize the weights and biases. We also need to keep track of the gradients, right? So the gradient will be a similar matrix. It will be exactly having the same shape as your weights and biases. So we are going to do that. And
do we need to keep the track of gradients, because can't we just initialize them every time we do the backward pass?
Good point. We can do that. Let me just check why I have done this here. I don't know why I have done this here. There's probably some reason behind that. I am not able to get hold of the reason now. Okay, for now we'll do this, but your question is valid. Right, your question is valid. So why do we need to do that? Something I also don't remember now, but
like it might require less space. That might be a reason.
Yeah, probably, right? So I'm not too sure of that, but your argument is valid, right? So every time you are finding the gradients, why not just initialize it at that time? Why have a list like this? Okay, but just for the sake of, okay, this seems to be better. Let's just stick to that. I'll call it GW and GB and G theta. Okay, so the gradients can be just zero values. So okay, so in the end, I'm going to return theta, G theta, W, B, GW, GB. Let's make sure that the whole thing works. GW is not defined. Okay, so is everyone getting what we are doing so far? What we have been doing so far? Any questions?
You haven't really reshaped the GWs.
Yeah, that also needs to be done. So, we have done it for W and B. We need to do a similar thing for the G theta and GB. All right. So once we have this in place, we have one major worry is removed, right? So we have the parameters, and can now go ahead and start looking at the forward and backward passes. So what will be the forward pass?
Calculation of the linear combination and the activation.
Yeah. So linear combination, and on top of that the activation. So we need the input and the feature matrix as well as the labels, right? For the forward pass, we need both. Do we need both?
We don't need the labels.
We don't need the labels, right?
Labels not needed. Yeah.
Just need the. Okay. Now, so the basic equation is what? Basic equation is Z equal to A W plus B, right? This is how it looks, and then A equal to G of Z. Okay, so these are the basic equations.
The A L of -1, is it?
Right. Yeah. So we'll now add all the structure. So this will be W of L, and this will be L minus 1. That will be for layer L, and A of L will be G of
ZL.
ZL. This will be B of L. Now this will be, whole thing will be in a loop, right? So for L in range of, so we start from 1, right? We have no weights and biases at layer L0. So we start from 1 and go all the way up to
Number of layers.
Right? So okay, so where is that information? That information is, let's say, in W. It's not the ideal way to do it, but if you had a class, we can do self dot number of layers. But anyway, yeah. So right. So now see, collab is complaining that Z and A are not defined, so we have to discover.
Colon is this.
Oh, okay. All right. Now we also need the Z values, right? So this is again these many matrices I need, and likewise. Okay, so finally I return something. I return A of -1, right? Okay, there are few missing things here. So can you fill it up? What are missing? What are the missing pieces here? Okay, first of all, we need W and B. It's not a class, so I need to pass W and B. So these two things are now disappeared. They have disappeared. I still have some. It's telling me that G is not defined. So let's go ahead and define G. See, G of Z. Let's just stick to ReLU. Okay, so ReLU is kind of easy. So let's say, how do you do ReLU?
Z greater than 0, it's Z or 0, right?
Max of
Max
0,
of 0 x.
Right. So it is just max of Z comma 0.
Yeah.
Okay, so this is ReLU. All right. So that fixes the errors, at least whatever errors that collab was pointing, the cell was pointing to. But there are still few logical errors. What can you spot them?
You need to initialize Z and A with the X, like the 0th element.
Correct, right? So the initial part is missing. So what would be A of 0? We have not yet specified, right? So A of 0 should be X. Only then the loop will get started. So now the loop will get started.
Sir, A of 0 is the input layer, na sir?
It's the input, yeah. Input activations.
Input activation. So it will contain all the features.
Yeah, it will contain the feature. It's basically the feature matrix.
So X is
X is the feature matrix, right?
so what I am thinking is so in the first layer the features will be separate. Like if I have 5 features, it will be separate node.
First layer, you are talking about the first hidden layer?
No, sir. So the input layer, in the input layer, if like the number of nodes is equal, or the number of neurons is equal to the number of features, correct?
Number of in the first in the input layer, the number of neurons equal to the number of features in the data.
Features. So where are we doing that? Like if we directly say A of 0 equal to X, it will take the whole matrix. But where we are differentiating that.
A of 0 equal to X, right? You need the whole matrix. It is the matrix view that we are looking at, right? AW. So basically it's like what we have been doing in all other models. It's XW plus B, right? If you think about SVMs, this is what we did in SVM, right? XW plus B. Instead of that, I'm calling it the activation into W plus B.
So X is a N cross M and W is a M cross 1.
It will be M cross whatever is the number of neurons, right? If there are 10 neurons, M cross 10.
Okay, sir. I understood. It's in the vector form. Okay.
Yeah.
Just a quick question. How is L equal to length of W? W has only features as the length, right?
So W is a matrix of, so list of matrices, right? So it's a list of weights. So I have as many elements as there are number of layers, if you recall. That's how we initialize.
Okay. Yeah, got it. Okay. Then it's the length. Fine. So I was just thinking of the weight matrix. Okay, got it.
Okay, so you also need to be careful about the weights here. So let's say you have n data points and A of L minus 1 will have what shape? It will be n cross something. If S is the architecture that we have, so what do you think will be the shape of AL minus 1? For n examples, what matrix will the activation matrix be? What shape will it have?
N comma N.
N comma M, but M is what here? For AL minus 1?
2. N would be the 2. Yeah.
Right, yeah. More generally for S, if you represent the architecture as S by this list S.
Number of neurons in that layer.
S of L minus 1.
Right. Should be S of L minus 1, right? Number of neurons in the L minus 1th layer is the number of features in that layer in some sense. And that is this is the shape, right? So what will be likewise, what will be the shape of W of L?
L minus 1 comma L.
S of L, right?
Yeah,
I hope all of you are getting this. See, this is kind of, we are doing this so that we know what we are multiplied, right? So these, now notice that these two matrices are compatible for multiplication. You get n cross SL minus 1, SL minus 1 cross SL. So you get n cross SL, right? So this product is
Yeah.
n cross SL. So we are so far so good. Now we are adding a vector of size SL, and thankfully they are compatible for addition according to NumPy's broadcasting rules. So recall that the NumPy broadcasting rule says that one of the rules is that the last index should be the same. Here we have only one index. This is a one-dimensional array, B of L, and this index, if it is same as this, then you can go ahead and add. So you don't need to reshape B or anything. No such gymnastics is required.
So B is not SL cross 1, right? Like in terms of NumPy.
No. This is not SL cross 1 because of the way we have not reshaped B, right? So we have, yeah, but that's a good point. It's not SL. So if had it been SL cross 1, I think it would have
transpose. It
Yeah.
won't broadcast. We would have to transpose.
Right. Okay, so I hope it's clear to all of you why we are doing this. So there's one more point which is missing. Can you tell me what we are missing here?
At the last layer, we have to like apply the output activation.
Exactly, right? So this is, we have to separate this into a hidden layer activation and output layer activation. So let's say the output layer activation is Softmax, right? Let's do that. So G out, I want it to be Softmax. So we have to write the Softmax function now. This is Z is of size n cross k. Okay, n examples, k classes. Now we have to compute the Softmax. How do we do that?
For I in range of k.
Okay, let's say I don't want to use loop. Can I still do that without a loop?
You have to initialize your. You'll have to take an exponential of z.
Okay, let me take np dot x of z. Okay.
Divided by np dot sum.
Okay.
You still have to loop it around.
Then np dot expz.
All right. Along what axis we have to sum?
1.
Axis equal to 1.
Is that all?
Is z equal.
Okay, actually this is all there is to it, right? Or are we missing something here?
So axis 1, you'll have to put it in the next bracket outside exponential, I think.
Correct. You are right. So that is correct. Are there any other errors like this? This is one error. There's one more error. So can you tell me what that could be? So look at the shapes. So what is the shape of the numerator?
N cross k.
N cross k. There is no problem there. What is the shape of the denominator?
It's just n.
And
Okay. So this is, we'll land up. So we have a problem here. So the denominator is of shape n. So this according to the broadcasting rules, the last indices don't match, right? So what I need to do is I need to simply reshape this as n cross 1. So once I do that, it's like dividing a matrix by a vector. And the nice thing is that this will be a vector of this vector will get broadcast across the columns of the numerator, which is what we want, right? So let me just write it down. The denominator so why is this useful? This is useful because to get the probability I need to divide each row by its sum, right? So there are
row sum.
and there are n rows, there are n sums, and I need to make sure that each row is divided by that particular sum of that row, which is what I have done here. Okay, so this is softmax. This is like, you don't need to loop. I mean, you can loop, of course, looping is not bad, but this is a pure NumPy way of doing it. Okay, I
So
hope.
whatever
In this case, the
function-
broadcasting doesn't follow that rule of having the last dimensions being equal, right?
That is the rule, but unfortunately here we don't have that. Before reshaping, we didn't have that.
No. So what I meant is, in spite of that, broadcasting still works because of, even though if it is n comma 1.
No, yeah. So there are two rules. There are two parts to the broadcasting rule, right? So one is that either you make sure that the last dimensions are equal, otherwise the last dimension should be 1. So we have made use of that second rule here.
Okay.
Okay, so see, honestly speaking, I don't understand it very well, but I know that these are the rules and we have to play by the rules.
Okay.
Right? So is this okay for everyone, softmax?
Yep.
Okay.
I think it's better to do it in vectorized form. It's easy because looping is messy.
Right. So the small change is that I will do g hidden of this. Okay, and so here alone, what I need to do is okay. So in fact, it's not enough if I return. So there are several points here which we need to understand. What all things do you? So what all objects do you think we need to return here? So forward pass will be followed by a backward pass. And what objects does the backward pass require? What parameters?
It will require the activation matrix, the activation thing for sure.
Right. So it will require actually the whole setup, right? It will require Z. It will also require A.
W.
W we have not changed, right? So W it requires, but we'll pass it separately. But from as a result of my forward pass, I or whatever is necessary for my backward pass, I need to get hold of those things. Okay, is this clear, everyone? What why we are doing this?
Yes.
Okay, so the backward pass is kind of boring to write because it's less easy to follow what's happening. Nevertheless, we'll go ahead and write it down. So we need x. So let me go and get hold of the equations of the backward pass. So you need to do this for every layer again.
So you need everything actually.
Right, we need the whole thing. So let me try to bring in some order here. X, Z, A, W, B.
Y and Y hat too.
Yeah, we need those fellows also. This is why we sometimes writing a class is better, because see how nice this is. We just need Y and Y hat. Okay, let me go ahead and Okay, so before that, we need to have y. Okay, let me add it. Let me insert it here. See, these are all useful functions for not just for this neural networks, but otherwise. That's why I'm writing them here. So, how do you encode your label matrix labels in this case?
One hot
One hot, right? So let's make sure we have a function for that also. So you pass the label vector as input and you return the one hot encoded matrix. Okay, so let's say y is something like this. Y might look something like 1, 0, 8. 8, so on and so forth. And now you have to return this whole thing. So I do it the following way. Maybe there are other ways to do it. So np.unique of y will return what?
Unique values in sorted order.
In sorted order, is it? Okay, so it will give me only so here it will give me 0 to 9, is it? Is that right?
No, it will give you the individual discrete numbers 0, 1, 4, 6, 8.
Okay.
Sorted order.
All right. So assuming that there are all 10 labels are there, it will give me, it will look like 0, 1 till 9, right?
Correct. Yeah.
Okay. So if I say that, then if I say that k equal to length of this, is that right? This will be the number of classes, right?
Yes.
Okay. So this is the number of classes. So what I'm going to do is I'm going to create an identity matrix of size k cross k, and I'm going to pass y as the index for that matrix, right? So it's like, I hope you all know that we can pass numpy arrays themselves as indices for another numpy array. So this will, I am claiming that this will return my one hot encoded matrix. Do you all agree?
Yeah.
Okay, so this is the one hot version. So you have your one hot, and assume that y is that one hot encoded value. Okay.
So do we have to write a function to generate y hat, or is it
yeah, good point. Yeah. So what do you think will be y hat from the forward pass?
argmax. The softmax function, right? So argmax of
Argmax
is 1.
Right, but
of a minus 1.
It will be a minus. It will be just a minus 1, right? We are
correct.
So we are not yet going to the inference part. So y hat, you are right in the sense that it's not the right variable name, but
okay, so this is just the softmax output then.
Yeah, it's just the softmax output.
Okay, so that's a minus 1.
Yeah, so that being the case, what I'll do is I'll get rid of x, because x is what a of 0 is x. So I already have that in some sense. W and B I certainly need. Y hat also I kind of have. It's like, it's not the right thing to do, but for demo it's okay. Y I anyway need, right? So what I'm going to do is I'm not going to write this code because it's just too many symbols out there. So I'm going to shamelessly copy this. Not shamelessly, because I kind of wrote this code, so I don't mind copying. Yeah, so you don't mind, right? I mean, this is like boring. You just have to look at the equations and just convert them into numpy arrays, numpy equivalents, right? Once we are done, I just go over them. But for that, it's like quite straightforward.
Excuse me, sir. May I
Yeah. Yeah.
So I was just following along, and since you have copied this one, so could you please share it in the chat if you don't mind?
You
So
want
that-
me to copy the paste
Yeah.
this thing in chat? Is it?
Yes, sir, yes. Actually, I was following along, so just wanted to have that also.
Okay. Yeah.
Oh, sure. Thank you so much.
I think the formatting is not retained. You may have to do the. I don't know why. Usually formatting is retained, right? When you paste. Anyway, so see what we are doing is these are the gradients for Z, gradients for A, and this is the gradient of Z at the outermost layer, which is going to be A y hat. Y hat is nothing but A of -1 in our case, minus Y. Okay, there are too many things you have to change them. So, are you all following what's happening? Or
You
do
go
you want-
line by line, I think it might be easier. Yeah, for when you correct one line by line.
Okay, so this is self dot layers, which is nothing but range of L. So this is gradients of the pre-activations, gradients of the activations. Now at the output layer, this is again formula, right? Y hat minus Y is the gradient at the output layer. If your pre-activations at the output layer, the gradients are
Yes.
Y hat minus Y. Now what we do is we start from the last layer and then we back propagate, right? So we start from the last layer and then go till the first layer. Okay, and so mind you, we stop at 1. So 0 is not included. So we stop at, so we need to compute the gradients for GW of L minus 1 all the way up to GW of 1. Right? We don't need GW of 0 because there is no such weight matrix. So where is GW in all this? Oh, these are also object variables.
You had set them up in the other one.
Yeah, so see, these unfortunately require they are mapped to the param. So I think I there's no other go but to do it as a class. Otherwise, it will be like it's be too foolish to keep passing around all these variables. I thought we could do it without classes, but I think it will not be the right thing to do. So I'm sorry, I have to do this. So all these become now attributes. Okay, so yeah, in the interest of time, I can just run the collab and show you what happens. Do you want me to redo the whole thing, or is it okay if we just run that collab and or go through that collab line by line? I can recreate the whole thing, but it's going to take us a lot of time. What do you all suggest?
Most of it is done, right? Like only.
Yeah, backward pass alone, maybe you might, if you can run through in the collab file.
Okay. See, yeah, you're right. Most of it is done. There's only the. Okay. See, most of it is done. So, what I'll just do is till this part. I hope you all follow, right? this part alone, I just go through the code, and I'm not going to recreate the whole thing because I would have wished to do it, but it's going to be little time consuming. So is that okay with everyone? Shall we start from the backward pass? And is it okay if I just show it to you?
Yes, sir.
Okay.
Okay.
Okay, so what's happening is, yeah, as we said, these are the gradients with respect to pre-activations, activations, and then this is your output gradient, right? So gradient in the output layer, and you start with that y hat minus y, you start with that, and then you keep going backwards. You start with layer capital L minus 1 in our case. So you start from the last layer, keep going back, and at each step, what you do is you update the weights, gradient of the weights, gradient of the biases, gradient of the activation, and then the gradient of the pre-activation. You do that in 4 steps. These 4 steps correspond to these 4 equations. Okay, so we'll first see what is happening at the weight matrix of layer L. Gradient of the weight matrix is A transpose into gradient of Z. Okay, that is what this is. A transpose into gradient of Z. Okay, so I hope this is okay. It's just straight substitution. Okay. Now the gradient of B is slightly tricky. See, Z is a matrix. Okay, but the gradient of B is going to be a vector. Okay. So do you see what is happening here?
So could you repeat this part?
Sorry, which part? This gradient of
B. Yeah.
Yeah. See, GB. What's happening is that, see, this is the expression that we have, right? So if you want to know how this expression comes, that's going to be a bit involved. So at this stage, I'm going to request you to trust me that this expression is correct. Once this expression is correct, one way of understanding what is happening is that, see, GB of L is going to be of the same size as B of L, which is going to be of size S of L. Okay, now I'm saying that gradient depends on the gradient of the pre-activations at that same layer. So it depends on GZ of L. Now, what is the size of GZ of L? It'll have the same size as Z of L, right?
Yeah.
Okay, that will be of what shape? The pre-activations at the Lth layer.
AL.
AL, okay. So it is a matrix, right? So it'll for n training examples, this will be the shape of the pre-activation matrix. Okay, now from this I need to get hold of S of L values.
So you're like just summing up the linear combination at every neuron.
Transposing it and summing it up.
Yeah, we are just summing. So we could have done it 2 ways. We could have done it without transposing. We should have summed it along axis 0.
Yeah, but then you will still have a shape which is.
Yeah, so what you are doing is, by transposing, what you are doing is you are getting it into this shape, S of L comma N. Okay, so each row represents one feature in some sense, right? So you're summing across the columns, basically. You're going from left to right. So you get hold of S of L values, which you store in GB of L. Right? If you sum this along the axis 1, you will end up with a vector of this shape, right? The second axis basically gets summed over.
Yes.
Okay, so I'm sorry, I know this sounds very, this seems very obscure, but that is the way it is, right? This, especially the backward pass, there are two difficulties which I'm sure some of you might be facing. One is the equations are themselves kind of weird, and on top of that, the code is also a bit weird. So the only way to understand this is if you sit down and write it. I don't think there's a better way of grasping this code. Okay, so this part is again just Z into W transpose, which is what we have done here. Z into transpose of W. And finally, this last equation is again, so this is instead of a matrix multiplication, it's just element wise multiplication, right? Hadamard product. So that Hadamard product becomes just a simple multiplication, element wise. And this is G prime of Z, right? G prime of Z. So I need some function which computes the gradient of my activation function, which is what this represents. Okay, so this part we can write, it's simple. Where did we write the ReLU? So what is it called here? Grad of G hidden, right? So let's call, if I call this G hidden, grad of G hidden will be what? Can someone tell me what it should be?
Max of 0, 1. I don't know. If it is positive, return.
Yeah, right. So our usual Z is greater than 0, return 1, else 0, right? So that is the derivative of the ReLU. Okay, so that is what this self dot grad G hid is. And that completes the backward pass. So one fine detail which I don't know how many of you noticed it. Do you see these extra colon P's? And do you understand why they have been added here?
Then place
GWL is in the shape of WL, right?
It's in the shape of WL, but why do I need this? I could have just said GWFL equal to this, right? Why do I need this colon business? Or if you leave that, if you just think about a vector, why do I need to do this?
then place something.
Exactly, right? You are doing it in place. Remember very early on what we suggested regarding this parameters, right? When I update my gradients, my theta should also be updated, right? Okay, so what is your backward pass computing?
The
So
theta.
you're essentially like taking a view and updating the original.
Right. So remember that this is computing gradients of several things, but most importantly, right? So the whole point of this function is to compute GW and GB, right? GZ, GA are all so collateral damage in some sense, right? They had to suffer because we had to compute GW and GB. See, our intention was not really to compute any of these fellows, but if you want to get hold of these two, you need to compute all the other things. That is the whole idea of back propagation. And why do you need GW and GB? Why do you need to compute these gradients?
Chain rule.
Gradient descent.
For gradient descent, right? You need gradients for gradient descent, which is why you are going after them. And if you need in neural networks, if you want GW and GB, you need to compute all this. Those, and the process or the method of computation is encoded in these 4 equations, which you can take off at this stage. For this course, you can take this as a rule of rule of law, right? This is how we have to compute the gradients.
Is it because chain of, chain rule, right? So if I want to compute the gradient first.
Yeah, the chain rule, yeah. So back propagation, so if you want this, you have to use the chain rule to compute all of them, and that is why you require the whole setup.
So that colon, right? Just going back to that. What it does is basically flattens GW of L, is it?
No, right? So it updates it in place. So I'll demonstrate that here using a small example. So let's say you have two vectors, right? A is one vector, and B is easier to take zeros, and B is a copy of A, right? And I mean a view of A. So something like this. I think what happens if I update A? If I update okay, so B is a view of B is a view of A. So now what have we done there? We're doing something like this, right? On the right you have one array and you are assigning it to some other array on the left. Okay, so I am assigning, let's do the same assignment normally. Let's say I do something like this. Now if I print A and B, what do you think the answers are going to be? If I run this code, what do you think will be the outputs?
Both should be 1, 1, 1.
Okay, so
well, B equal to A. Then you update the A, so B should also show the updated values.
Okay, let us see.
Oh no, my God.
Okay, right. So see what is happening is when I say B equal to A, so far so good, right? Here at this stage, till now, we can say that B is a view of A, right? So B and A are essentially pointing to the same memory location, and B and A are essentially the same. But here in line 4, what I do is I completely change the nature of A, and I kind of recreate or create a new array and assign that to A.
Oh, I see. So here the A's memory is actually changing. Like
it's actually changing.
Yeah, got it. Right.
Okay. So in order to preserve that, in order to not destroy the link between A and B, I have to do this kind of an update in place, right? So what this is saying is that, hey, don't destroy A, just whatever values of A are there, just replace them with 1, 1, 1 in the same memory location.
Oh, beautiful. Yeah.
Okay, so this is what we are doing here. We are not destroying GW, the link between GW and G theta, which is the link I have created when I initialized my parameters. I created a link between GW and G theta, right? So GW and G theta, the link was created here. Now, when I'm doing my backward pass, I don't want to destroy that link, which is why I do all this.
Now it makes sense. Yep.
Okay, so that is.
And the GW is a flattened thing, or is it a matrix?
GW is a matrix, right? So this is so here, that's why I do colon, comma, colon, because I need both dimensions to get assigned this array. I want to assign it to the entire thing, right? Not just to one dimension.
So here, so just going back to our original example, here we are actually updating B and getting, so let's say A is your flattened list, right?
Okay.
Of gradients. And then from that you have reshaped and you've got the matrix of gradients.
Okay.
Now in this code, you're actually updating the matrix, right? The matrix itself, not the flattened.
No, yeah, you are right. Yeah. So, yeah. So here what I'm doing is, yeah, that's a good point. Why I'm doing it this way is, in the backward pass, I don't have access to my theta. I mean, I only have access to my weights and biases, right? So I can only compute their gradients, and I can only update them. And I want this update to be reflected in my parameter vector, so that when I do gradient descent, I can do the self dot theta equal to learning rate, whatever, that minus gradient into learning rate.
So this is kind of going backwards now. So what happens is, first you're doing A, flattened, it's a vector. From that you create a matrix B. Now you're updating B and it gets reflected back in A, is it? Is that how it works?
Yeah, exactly. Yeah, and then what you do is you update theta, so you are changing W and B.
Right.
Right, and you're using that W and B to compute GWGB, which changes G theta, and then the cycle continues.
Okay, so which means you're actually updating the view, which updates the original.
Yeah, you're updating the view. Exactly.
Right. So both ways it works. It's not just that you'll have to update the original to get it reflected in view.
Right. So to summarize what you have told so far, in the backward pass we update the views of the gradients. Right. In the
Forward pass.
In the fit, what we do is we update the views of the weight vector. We don't update the views, rather we update the original vector, and that gets reflected in the views of W and B. Okay, so far that's what we have done, and now fit is actually very simple. So you accept X and Y, then these are default parameters, like in any gradient descent update rule. You go through set number of epochs, you first do the forward pass. So forward pass returns Y hat, right? So this forward pass, if you notice, is just you return the last value in the activation list, right? And that is your Y hat. Okay, so that is the forward pass. So in fit, what happens if you, so you compute the forward pass, you execute the forward pass, get hold of the Y hat, and then you calculate the loss, which we haven't gone through, but loss is pretty standard. So
this is some squared error for regression
and this categorical cross entropy for classification. Okay, so this part may be new. We shuffle the data set. This is something we haven't done that much. See, we shuffle the data set before gradient descent because we want a random sample. We want to choose a random sample and update the gradients, right? So we are running mini batch gradient descent. So if your mini batch is, let's say, of size 32 or something like that, now you want to ensure that these 32 samples that you are drawing from your data set are randomly chosen, right? And for that reason, you shuffle your data set once before each epoch. Okay, so otherwise what will happen is there is a possibility of presenting all samples that belong to a same class, right? So for example, that might come up. You don't want something like that. So you want, one of your assumptions, if you remember, is this IID has been something we have been keeping up all along. So I want to present as random a sample as possible. Okay, so I create these random samples and then run mini batch gradient descent. So in each mini batch gradient descent, I'll have to do one forward pass, one backward pass, and then update my parameters. So depending on the number of batches, I will do that many updates to my parameter theta. Okay, so this is the core of the code for neural networks. Do you have any questions at any stage?
Excuse me, sir. May I ask
Yeah.
a question?
Yeah.
This is regarding the softmax function that we have wrote above. So
Yeah.
I was having trouble with that axis. I'm not able to get hold of why we are doing it along the first axis. I mean, it should be 0, no? Because my reasoning is that since we have n rows, and what we essentially do is we do, np.exp of z, and we sum it across. I mean, we need to sum the rows and not the columns. So if we do axis is equal to 1, sums of the columns. So why is it that we are doing it? I mean, for the columns, shouldn't it be rows?
So see, the softmax represents what? It represents for each example, it represents a vector of probabilities, right?
Right, sir.
Belonging to each of the k classes.
Right. So what I want my output to be is, let's call this output O. So O of I want it to be a vector of k probabilities which sum to 1.
Right, sir.
Which sum to 1, which is this what I desire. So now how do I do that? I have exp of z, so I compute the exponent of z, and I need to sum, so I need to divide the k values for each row by its sum, right? So I need to divide, let's say, to take a concrete example, let's take these as the input. So input is in fact we can just take one np dot array of 1 2 3 3, say this is 3 1 4 3 1 whatever, minus 1 is also valid in this. This is, say, class 2. It is class 2. This should be something like 1 2 1. So this is my input, right? This is 3 cross 3, so it may add to confusion. Let's do it 4 cross 3. So 0 1 1. So there are 4 training examples and 3 classes. So let's see what we have to do here. I have to do e power 1 for the first example. What do I have to do? I have to do np dot right. So I have to do this.
Right, okay, so we are summing across k actually. We're getting
yeah.
Okay. The axis, I mean, axis is equal to 1 is essentially k. Is that right?
Yeah, that is right. Across the k columns, you are summing it.
Across the classes, we have to sum, and then we'll get the probability of that example belonging to that particular class. I mean, for that example, the probability of that example belonging to each of those classes.
Each of those classes, yeah.
Yeah, I understand. Okay, understood. Thank you.
Yeah. So any other? So if you run it, right? So if you run the whole thing, it will be like just like any other method we have seen so far. The loss will decrease, and then you can compute the accuracy, and you can actually play around with this. I think one of the students, Venkatesh or someone, I think Parth has also shared, but more recently Vishwajit has shared his. I think it's very similar to what we have in the collab here. Okay, so you can take a look at that, right? So it's the same thing essentially. Most of it is similar. You can download this collab and try to play around with that. Right, so it's there on this course. The link is there. I think it's been pinned, so all of you will be able to access. Okay, any other questions specifically regarding ANNs?
Is neural networks part of OPP?
No, it is not. Right, it is not. But there are some useful functions which are lurking there, which might be of use.
Yeah.
Okay, so if there are no other questions, I would just like to do a quick round of thanks to. I mean, this is potentially the last session. We may have one revision session, but I am not sure if I'll be around because see, we have already done 3 rounds of week 12, so there's nothing much to revise per se. So mostly Nitin will be taking that final session. So from my side, I think this is the last session for MLT, and I would like to thank, many of you, and just call out these names in alphabetical order, right? So Abhishek, Afnan, Devasmith, Kaushik, Parth, Sunita, and Vivek. Vivek, unfortunately, I don't think he's here today, but of course, all the others who are part of the session, thank you. So, why I wanted to do this is because of this, right? So, even if the numbers are small, I think some of you who join, you make sure that you keep the session kind of lively by asking questions, and I really appreciate that effort from your side. I think some of you here have attended every single session, if I'm not wrong. I've seen you in all of these sessions, so that shows your kind of commitment. And even if it's Saturday, Sunday, or very late in the night, I've seen all of you attend these sessions, and I really thank you for your presence here because it's tough to talk to a non-responsive audience, right? And whenever you respond, I think it like really shows that you're engaged and not here just for some bonus marks or things like that, and you genuinely want to learn, and I appreciate that a lot.
So that helps you to calculate your gradient.
Yeah, right. Yeah, that kind
So
of.
it's mostly because of how much effort you put into from your side before these sessions, like extra efforts like preparing slides and notes.
So attending these sessions are also very helpful because sometimes the videos are dense, right? So here it's kind of diluted version, and we get sufficient time to really understand in detail, and we can ask questions, right? Which you can't do that to the course video. So attending these kind of sessions actually help us understand the concepts very, very well. So really appreciate you actually taking time and explaining, even if it is a small audience. Really appreciate your contribution.
Thank you, right. So in fact, I'm happy that it's a small audience. It's not that the larger crowd will be disturbing, but see, even if it's a small audience, it's like a kind of a committed audience, right? So that is very important.
You almost have a set of fans now.
Oh, right. Thank you.
All the
No, I
cake, right?
Yeah, no, I think it's been
Next
excellent.
Paradox, Karthik sir would have a like autograph stall.
Yeah, I think.
Next time in Paradox, sir. 2022.
2023.
23
Yeah.
rather. Sorry.
Sir,
Yeah.
I just had one question. Like
Yeah.
now, almost like all the algorithms are over. Like we coded them very naively. So in practice, if you ever had like chance to encounter some efficient implementations, are there any like specific data structures which are used for these algorithms?
See, the interesting part I would say is that if you look at a typical ML job or ML course, right, they rarely do this part of coding from scratch in NumPy. Okay, mostly what happens is they just give you a data set and you use sklearn or TensorFlow and you just dump your model on top of that data set, or you dump your data set on top of the model, and some accuracy you present and precision recall, and then you get away. That's what is usually done in practice. But what exactly goes into building these models. The backend stuff, usually we don't explore it that much, right? So to a specific question of what data structures are used, I am actually not that aware of it. But there is a degree course that is coming up after deep learning, which is called Deep Learning Practice, where I believe they are going to explore certain aspects of how these networks are actually implemented, how to make these computations faster, and all that.
Yeah, because most of those things are open source, they would also like us to contribute to the open source and become part of the
Yeah,
development
that's
community.
actually like if you go and look at like a sklearn's implementation or something, like it would be really confusing at first to even grasp what is happening there, even though you know the theory behind it.
Agreed. Yeah. So, yeah, that happens, but mostly we won't be looking at them. It's up to you to explore these things, right? So, anything. So yeah. So some general feedback. What now that we have completed the course? What did you feel? How was it? Because live session parts you have commented, but otherwise, did you get a feel of learning some machine learning?
So do you want us to comment on the videos or?
Okay, not the videos because that we have discussed in this course. But in general, do you have a feel of what ML is now?
Definitely, sir, because I can talk like a working professional. We have all used deep learning, keras, and all that. And that was like a black box. I mean, we know exactly what it is doing, like input and output, and we get it. So we know enough to write the code and get the output. But now in this course, MLF kind of did the foundation, like the math. But in this particularly MLT, we really understood how each layer is happening, how the weights are getting updated, biases are getting updated, and the process of updating it forward and backward. I think that really shows. It's almost like we are driving a car without knowing how the engine is operating, right? Now we opened the hood, we looked at it. Okay, there is a connecting rod, there is a piston, then there's a cycle. Now you suddenly understand the same car you were driving before. Now you suddenly feel like you understand what's going on now. So I think this course also gives you that level of confidence and insight into how really the numbers are represented at matrices and vectors, and how they're end of the day are used to what I call as function approximations, because end of the day everything we're doing is curve fitting basically, right?
Right.
I think the video that Parth shared last week was very beautiful, right? So any nonlinear curve, how you can express it as a linear combination of weighted approximations, right? So the more nonlinear it is, you just have to have large matrix, right? So all those concepts are very, very useful. Now, putting this course into context really helps us to have a very solid foundation. I think that's what this course, this is exactly is where how this particular course is different from all of the courses offered in our country at this moment. I don't think any other course that I've come across goes into such technical depth, because I think most of the students will run away by this time, right? So, but I think this is really lovely that IIT Madras is putting together such a high level, high quality course.
Okay, got it. Thanks, Nick.
What I've mainly learned from the course is like when you're using a sklearn or something in your particular data set, if there's like a model that is you expect to behave a certain way and it is not behaving that certain way. Before this course, I didn't really know like why that was happening, but now it's like a fairly good idea of why that might be happening, what in the data might be causing that.
Right. Yeah. That's so debugging for ML, right? That's a tough part. Yeah, I agree. So it can be really hard. Okay, so I would kind of stay back in MLT. I don't know, and I'll be meeting you probably in some degree course in January, not before that. So until then, I think it's goodbye.
In MLP, you won't be there.
Sorry? In MLP? No. MLP, I won't be a part of MLP next term. Even this term, I'm just in MLT, right? So
Would you be doing the deep learning? Hopefully.
no, deep learning will be taken by another instructor. Reinforcement learning is a course that I'll be a part of in Jan 2023 when it is
Okay.
first offered. Yeah. But otherwise, you can all keep in touch and reach out to me in case of anything that you need.
Do you
Right?
take PDSA still, sir?
PDSA, no. PDSA, again, I was there only for a brief while. So
Okay.
then I moved to MLT.
Okay, sir.
Now we'll probably meet like the next term this year, because for me almost all my data science courses are over, so it's programming now.
Oh, okay. So you are doing one diploma at a time, is it?
No, I was just doing, but the more data science courses are completed.
Okay.
So now programming are left mainly.
All right. Okay. So I hope to meet some of you. Please do come down next time. Yeah. So next time.
Sir, I met you in Paradox near
Yeah. I met Deva Smith and Parth, right? And I think Kaushik also I met.
Yeah, we met.
We met. So in the ICSR building itself, I think we met. Others, I think I haven't met so far. So if you get a chance, anytime, please come down to ITM. We can meet, or I think the next Paradox will happen. I don't know when, but
month of May, most likely.
yeah. All right then. So
Thanks a lot, sir.
Thank you so
Thanks
much.
a lot.
Thank you for all the
Enjoy.
effort.
Thank you so much, sir.
Thanks.
Yeah.
All the very best to everyone.
Yeah, thanks.
Thank you, sir.
Yeah. Thank you.